Greetings, Glenn here from West Valley College. Today, let's learn about VSEPR theory, valence shell electron pair repulsion theory. Again, VSEPR. Sometimes we say that as VSEPR theory. This is all about the shapes of covalent molecules. So, for example, here's a water molecule, H2O. How come it has that bent shape? Is there a way that we could have known from the chemical formula that it is going to be bent? And there is. So there's this theory. We start with a good Lewis structure. We apply VSEPR theory. We can make a very accurate prediction about the overall shape of it. It's a pretty complicated sounding theory, but ultimately the idea is that groups of electrons repel each other to determine the shape of these covalent compounds. And you might be wondering, well, why do we care so much about the shape of a molecule? Well, for one, I think it's a lot easier to imagine what's going on in chemistry if you can think about the shape. It's a lot easier to imagine a reaction with the water molecule if you're picturing this shape, but rather than just the chemical formula. But then on top of that, one thing that you're going to learn a lot about the further you go in science is structure-function relationships. The shape of water determines all of its properties, determines what we can use it for, its boiling point, its melting point, what does it fit with. The shape determines whether a medicine can fit with the protein that it's supposed to interact with, or a poison and how it works. So structure function is kind of like key and lock. The shape of a molecule determines its properties, which then determines its uses for us. So let's dive into it a little bit. So here we can see our 5 basic shapes. And these are all about the central atom and how many electron groups are around that central atom. And so you got your first example, BeCl2. Once you draw the Lewis structure, you see that it's got 2 electron groups around it. Each chlorine acts as 1 electron group. And those electron groups spread out as much as possible. Again, electron groups repel each other to determine the shape. So those chlorines will spread out to the maximum angle, and that angle ends up being 180. So here I've got an example. We kind of resort to balloons here a lot of the time to talk about shape. So in the middle is the beryllium, and on the outside is the 2 chlorines. And I can maybe cram them together into a weird angle for a second, but it always ends up bouncing back to this 180-degree angle. That's just kind of where they're spending most of the time. So again, these balloons are showing the bonds between the beryllium and the chlorine, and those bonds are going to spread out. The electrons repel each other. They don't want to spend a lot of time in the same space. And so they spread out, and this is the lowest energy orientation for these 3 atoms and the electrons, 4 electrons holding them together. And again, with just 2 electron groups, we call that linear. And linear represents, or is represented by a 180-degree bond angle. What happens if we add a 3rd electron group in? So if I get my 3rd balloon up here and I try and cram it in, the other 2 can't stay linear and maximize all the angles. It comes in and it affects one side a lot more than the other. So as it comes in, it crams everything over. Let me get this electron group bonded in here. And so now we've got, a lot of people will say things that like triangle. You got 3 electron groups. So the example that we're using here is BF3, boron trifluoride. So again, the boron's in the middle, it's the central atom, 3 fluorines on the outside, and these are the single bonds, 2 electrons in a single bond between the boron and 1 fluorine. Boron in the middle, fluorine, boron, fluorine. And those 3 electron groups, those 3 bonding electron groups, spread out as much as possible. And again, I can maybe temporarily cram some things together or force them all close to each other, but this is the lowest energy place for these electron groups to be, with a 120-degree bond angle. So 120, 120, and 120. Then you also notice that this molecule is very flat. All 4 atoms are in the same plane. So that's why we call this trigonal planar. So 2 electron groups was linear, 3 electron groups is trigonal planar. What happens if we try to cram a 4th one in? It doesn't really matter where I try and cram this 4th one in. I could try and weasel it down under here under the plane. A lot of people will make the prediction. So if I asked you, well, what do you think the bond angles will be with 4 electron groups? A lot of people will start guessing 90. They make the assumption that all 4 of these are going to stay in the plane still. So let's see what happens. We're going to try and cram this one in. Okay, it's flat, but then when we let go, something very interesting happens. You hold it like this, it almost looks like you got 3 on the bottom and 1 sticking up. And it doesn't really matter which way you turn it, it's always the same. And what you might also notice, if you get your compasses out, you'll see that the angle isn't 90 anymore. It's more than that. It's 109.5. What you also notice is that all 4 atoms aren't in the plane anymore. So this is representing CH4. I got carbon in the middle, hydrogen, 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 4 hydrogens. And again, the balloons aren't representing the atoms. They're representing the bonds between the atoms. So carbon in the middle, H out here. I don't have anything showing those. We're just looking at the bonds and how they push each other out of their way to adopt this lowest energy conformation. We call this tetrahedral. There's 4 points. 1, 2, 3, 4. There's 4 faces, a bottom face, this front face towards you, 1 towards me, and then 1 back over here, 4 faces. There's actually a very interesting shape in geometry called the tetrahedron. A lot of things are made like tetrahedrons, for example, like kids' toys, and maybe even dog toys. So 2 electron groups linear, 3 electron groups trigonal planar, 4 electron groups tetrahedral, and again, this ideal bond angle is 109.5. I usually don't go up to 5 or 6 with balloons, but if you cram a 5th electron group around the central atom, it's going to sneak in down here. It forces the original 3 into a plane, and now you got 1 below and 1 above, and that's called trigonal bipyramidal. Trigonal bipyramidal is interesting because of the 5. It's the only one that has 2 different angles. It has 1 set of angles that are 90. Let me go back to the picture over here. So it's got so these 3 that are around the middle here, that's called the equator. Those are called equatorial positions. And then the 1 above and the 1 below, those are called axial. They're along the axis. Kind of imagine it like the Earth spinning around. And the angle between any axial and any equatorial is 90. And then the angle between any 2 equatorial is 120. So a good example of that is this PCl5. And then the 6th one, if you try to cram a 6th electron group around a central atom, you'll get octahedral. This is where you get 4 sort of around the middle, 1 above, 1 below. But the really interesting thing about this is that if you turn it in any way, it's the same. All of the bond angles are 90. And an example of that is SF6. So trigonal bipyramidal is the only one that really has sort of a direction to it, where if you turn it like this, now the axial would be left and right. So trigonal bipyramidal is very interesting. The other 4 only have 1 angle associated with them. The key thing that you need to be able to do to use VSEPR is take any formula for a covalent compound, and then using a good Lewis structure, be able to predict what the geometry of the central atom will be. So to do that, you gotta start with the chemical formula, draw a Lewis structure, and just count the electron groups around that central atom. The key thing here is that every lone pair, single bond, double bond, or triple bond counts as 1 electron group, or 1 electron group only. And that feels a little foreign at first to some people, because we know that a lone pair has 2 electrons, a single bond has 2 electrons, a double bond has now 4 electrons, and a triple bond has 6 electrons. So it feels kind of weird that those are all count as just one, but this is one electron group. Even if it was a double bond, it's one place where electrons are between the central atom and the terminal atom. And it's going to behave as one group, and it's going to push the other terminal atoms out of the way as one group. So here, now we can, now that you've seen 5 examples, you've seen the balloons, we've got the examples right there, we can try a couple. What is the electron geometry and bond angle around the central atom in the following covalent compounds? Feel free to try at home. You might even pause the video and try these on your own and then see what I come up with. So again, I got to draw a good Lewis structure first. So I'm sort of assuming that Lewis structures are something you're familiar with here. You start by counting electrons, 1 for hydrogen, 4 for carbon, 5 for nitrogen. Again, those are valence electrons for these nonmetals. So that means we've got 10 total electrons. It's a good idea to assume that the connectivity of the molecule is the same as the way it was written. If it wasn't H connected to C, then connected to N, we would have written it in a slightly different way. So H usually, then C, then N. And this is our sort of basic structure. We've just connected them with single bonds. And when we did that, we used 4 electrons. So now 6 electrons are left over. Now we're going to start putting these extra electrons as lone pairs on the terminal atoms first. You don't put them on the central atom until all the outside atoms are sort of satisfied. Remember, hydrogen is the first row nonmetal, and it only needs 2 electrons to fill up that first shell to get up to 1s2. So it's actually good with the single bond. You will always see hydrogen in covalent bonds with just a single bond. You'll never see hydrogen with a single bond and maybe like a lone pair or 2 or 3 lone pairs. You'll never see hydrogen with double or triple bond. Those just do not exist. Those are more than 2 electrons. This is the only way that hydrogen can be part of a covalent bond. So it's got its 2 electrons, but nitrogen, on the other hand, is in the second row. It wants to fill up S2 and all 3 of the P's. So it needs 8 total electrons, 2 in S, 6 in the P's. So it's got 2 in the bond. So now now I'm putting lone pairs in. So 4, 6, 8. That I put in 6 more electrons. I've run out of electrons. A lot of people, when they're first starting out with Lewis structures, they might end the problem early. Wow, it asked me to draw HCN. I know HCN has 10 electrons. Here's 10 electrons. But this is too early because carbon doesn't have a complete octet. It doesn't have a noble gas electron configuration. Right now, carbon only has 4 electrons. We got to get it up to 8 too. Some people might take a wrong turn through the maze of this problem and just start slapping in some extra electrons. You can't do that either. We had only 10 valence electrons. If I started adding electrons, that would be HCN minus, and then -2, -3, -4. So at this point, we can steal some electrons from that nitrogen. We're out of electrons. Carbon needs 4 more. So I'm going to bring one of these lone pairs. I'm going to bring it in. Nitrogen needs it, but carbon also needs it. So they're going to share it. Instead of a single bond, it's going to be a double. That would be then 6 electrons for carbon. So we're also going to bring in this lone pair too. So we're going to draw a resonance structure. We've just moved electrons so far. And now there's a triple bond around carbon. Carbon has 8 electrons, nitrogen has 8 electrons, but the H only has 2. This is the best Lewis structure for HCN. So we draw a Lewis structure and then we count electron groups. We got 2 regions of electrons. We got a single bond over here. We got a triple bond over there. That looks an awful lot like 1, 2 electron groups. I'm going to get rid of those numbers because we don't really need those. 2 electron groups looks like, looks like a linear geometry, right? We got 1, 2 around the central atom. So it's going to look very similar to that first balloon structure I had. HCN down here, we can make a very reasonable assumption that it's going to have a 180-degree bond angle around that central atom. So it's got a electron geometry of linear. Those are actually synonymous. If you say a central atom has a 180-degree bond angle, you're saying it's linear, and vice versa. So let's dive into this next one. This next one's kind of interesting. This is nitrate polyatomic ion, and it's got that negative charge, which means we need to add that electron into our count. And so the nitrogen still brings 5 valence electrons. Each oxygen brings 6, but there's 3 oxygens. And then we'll add one more for the negative charge. That negative charge just kind of gets spread out over the molecule. It's helping all of the atoms achieve that noble gas electron configuration. So now we're up to 24 valence electrons. Again, we'll put nitrogen in the middle. We'll connect these terminal oxygens with single bonds that used 6 electrons, so we're up to 18. We're always going to fill up the terminal atoms first. Each of those terminal oxygens only has 2 electrons right now. They need 6 more to get up to 8. I would never want to start by adding lone pairs on the central atom. It's very hard to get the correct Lewis structure by starting with the central atom. So always start with the terminal atoms. So we'll put 1, 2, 3 lone pairs on each oxygen. That's 6 extra electrons. That brings all of the oxygens up to 8. That uses all of the valence electrons. That used all 24. And yes, all of the oxygens have 8 valence electrons, so they all have that complete octet. But now the nitrogen only has 6. So we're going to have to do the same thing we did before. We're going to have to bring 1 in. Notice I'm using that double-headed arrow and a resonance arrow to show those electrons moving. And you might remember that we also need to put this polyatomic ion in square brackets with a minus charge here. So now the best Lewis structure for the nitrate polyatomic ion. And hopefully you're screaming at me through your computer that this has resonance. I picked that oxygen on the left. You may have picked that oxygen on the right to donate that extra lone pair to make the double bond. Somebody else might have picked the oxygen on the right. All of them are equal. All of them are the same. There are 2 other resonance arrows, 2 other structures to show the complete Lewis structure for nitrate. Okay, so again, you got to draw a good Lewis structure. Sometimes resonance is part of that. I'm not going to dig too deep into resonance structures right now. And again, now we can count those electron groups. Remember, double bonds also just count as 1 electron group. So I got 1 electron group, 2, 3. Nitrogen was the central atom. It's between 2 or more other atoms. So nitrogen was central, and I saw 1, 2, 3 electron groups around it. 3 electron groups is a trigonal planar geometry, is 120. This molecule will have a very similar shape to BF3, except it has a charge. BF3 was neutral. So what is the electron geometry and bond angle around the central atom? Well, now we know. We drew a good Lewis structure. We counted electron groups. We said, oh, 3 electron groups is trigonal planar and has 120-degree bond angle. Let's keep going. 2 more here. COH2. One thing that I really want you to notice is that you can't just look at a chemical formula and know what the electron geometry of the bond angle is. COH2, well, first we got to think about what the connectivity is going to be to make sure everything's got a complete octet. And this is one of those weird scenarios. I just told you that HCN was connected in the order that they were shown. In this example, the H's are not connected to that oxygen. It's really hard. It's impossible to get a good structure with both H's on the oxygen. It's really hard to get a good structure with even 1 hydrogen on oxygen. A lot of times carbon is just written as the first one. So carbon brings 4, oxygen brings 6, each hydrogen brings 2. Each hydrogen brings 1, but there's 2 of them. So we got 12 valence electrons. One guideline that you might remember is that the least electronegative, the one that's closest to the staircase, the one that's most metallic, the one that's furthest away from helium, is going to most likely be in the center. So we're going to put our carbon in the middle, and we'll connect the oxygens with the oxygen to the carbon and the hydrogens to the carbon. It wouldn't have been like the worst thing to do something like this. If you use formal charge, you would see that it's really hard to get, it's impossible to get a good Lewis structure this way. So that's why the oxygen, it's yet another reason why oxygen isn't central. Eventually you would settle on this structure, getting all of those formal charges down to 0. Again, I've used 6 electrons putting these 3 atoms around. There's 6 more. The hydrogens, just like in the first example, are satisfied with 2. 1s2 is full. They have a helium noble gas electron configuration, but oxygen has only 2. So we need 2 more to get up. It's got 2 in the bond. It needs 3 lone pairs. It needs 6 electrons to get up to 8. And that uses all 6. I'm out of electrons. And so again, we're looking at that central atom and seeing that it's not quite at 8. It's got 3 bonds. That's 6 electrons. It needs 2 more to get up to 8. So this is actually very similar to the previous one. It's just missing the only difference is nitrate is charged and here it's not. So again, I'm drawing my resonance structure, a better resonance structure, because right now the formal charges are 0 for hydrogen. Carbon doesn't even have a noble gas configuration, so it's not a good structure anyway, but it's 4 minus half of 6, so it's plus 1. And oxygen 6 minus 6 and half of 1, so minus 1. So that's why we feel confident in drawing this other resonance structure with a double bond between the C and the O. First, because hydrogen has an octet. Oxygen and carbon have an octet. And second, because now all of the formal charges are 0. So this is much more stable. This is much more likely way to find formaldehyde. And same thing as nitrate. We got 1, 2, 3 electron groups. And so this is also trigonal planar 120. Number of electron groups determines the electron geometry, the shape. Determines the bond angles. Each of these is 120, ideally. So up here, we could have said that, yes, for sure, they're 120 because all of the terminal atoms are the same. Down here, it's not going to be quite 120. Which atom is bigger, oxygen or hydrogen? Hopefully you said oxygen is bigger because hydrogen is the smallest atom. And since oxygen takes up a little bit more space than the hydrogens, this is actually, the bottom angle is going to be a little bit less than 120. So that's a less than 120. And the OCH, each of those is going to be a little bit more than 120. But altogether, it'll be 360. It'll still be planar, still be 3 points, still be trigonal planar. So the reason I wanted to show you this one is if the terminal atoms are a little bit different, they're going to skew the angles a little bit. For each individual molecule, you'd have to, go and do X-ray crystallography or look it up in a textbook and then memorize it if you wanted to know. But we're just sort of noticing that it's not going to be ideal because oxygen's a little bit bigger. Again, if I have 4 electron groups, it would be tetrahedral. If I have 5 electron groups, it'd be trigonal bipyramidal. If it was 6 electron groups, it would be octahedral. So we got one more here, IF5. Iodine brings 7 valence electrons. Each fluorine also brings 7, and there's 5 of them. So this is 42 valence electrons we have to worry about. So we're going to put iodide in the middle. Fluorine is the most electronegative, so it's definitely terminal. This is a very weird structure at first because you might get to here and say, well, now iodide has 8. Where do I put this 5th fluorine? A lot of people will try to cram a fluorine in here. And at first that looks really good because, again, it keeps iodine at 8 and we'll be able to put all these lone pairs around it. The problem with this is it introduces a fluorine-fluorine bond. And again, if you go back and use formal charges, we'll find that the central fluorine over here has a +1, even though it's the most electronegative atom here. So you're asking an electronegative atom to carry a positive formal charge. This doesn't ever happen. I can't recall a stable molecule that has a central fluorine atom connected to another fluorine. It just doesn't happen. Fluorine is too greedy with its electrons and can't form two bonds or even a double bond. So actually our only choice is to cram in one extra fluorine around the iodide. IF5 is a stable at maybe certain temperatures molecule. And then again, at first, this is going to feel very weird because how many electrons are around the iodide? Remember, there's 2 electrons in every bond. So you got 2, 4, 6, 8, 10 electrons around iodine. So this is one of those octet rule exceptions. And that's true for both of these. These are octet rule exceptions. These are pretty rare. Of all of the stable molecules that we know, again, there's a huge percentage of them have carbon in the middle. And carbon is always linear, trigonal planar, or tetrahedral. It's in the second row. It's got to follow the octet rule. So well over 90% of the covalent molecules are either linear, trigonal planar, or tetrahedral and follow the octet rule. There's a few stable molecules. Again, they're going to have a third row nonmetal or lower. Phosphorus, sulfur, chlorine, selenium, bromine, iodine. These are basically your 6, maybe arsenic, maybe antimony. Those are metalloids. These are your 6 nonmetals that might be central in a molecule with more than 4 electron groups. Because again, you might not have noticed the first time we went through this, but PCl5, same thing here. The phosphorus has 10 electrons around it and no lone pairs, so 10 total electrons around it in the valent shell. And sulfur has 6 bonds, so 12 electrons. So they're both octet rule exceptions, and they're both on this list of 6 that you might find in the middle. And down here, we've got iodine in the middle. So that used 10 electrons. So now there's 32 extra electrons, and I'm going to fill up those terminal atoms first. So fluorine, each fluorine has 2 in a bond. They need 6 more electrons in 3 lone pairs to get up to 8 to have an octet. And 6 times 5 is 30. So there's 2 extra electrons here. What do I do with 2 extra electrons? You might remember from drawing a good Lewis structure that you put those lone pairs on the terminal atoms first, and then once all those terminal atoms have their octet rule satisfied, then you put those leftover ones on the center atom. And some of you are getting a little concerned right now because we already said iodine was full and beyond full. It's an octet rule exception with 10 valence electrons. But now we got these 2 leftovers. They got to go somewhere. Fluorine's satisfied with 8. So we're just going to put them on the central atom as an extra lone pair. And that feels very bizarre at first. But again, we just saw that 12 electrons is fine for octet rule exceptions when these 6 atoms are central. And there's iodide again. So iodide is in the middle. And now we can count the electron groups. Each single bond is 1 electron group, and the lone pair is also 1 electron group. So we've got 6 electron groups. 6 electron groups means that they're going to spread out and adopt this octahedral geometry, which means the angles here are going to be 90. You might be wondering, well, since we just talked about formaldehyde, COH2, and how that oxygen took up more space, and over here on the iodide, I see 2 different terminal groups. I see fluorine atoms and a lone pair. Does one of those take up more space than the other? And yes, probably the lone pair, because it's not shared between atoms, will take up a little bit more space than the bonds to fluorine. So it's going to kind of push in, crowd in, and force the other bonds to be a little bit less than 90. So when the terminal atoms are different, you're probably okay saying that the angle is going to be a little bit less than ideal, because if they're different, that means one's bigger, takes up more space, which means the other ones are going to have to accommodate that and be a little bit less than ideal. And so here was 4 example molecules of using VSEPR. And again, the key thing that we're using here is actually a skill that you already picked up, drawing a good Lewis structure. So you got to be able to draw a good Lewis structure. Then you can look at a chemical formula. Everybody can count those electron groups, 2, 3, 4, 5, or 6. And then based on those number of electron groups, you know the geometry: linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. I hope you feel confident in applying VSEPR theory to molecules on exams, tests in the future. Be good, learn a lot, and have fun.